All right, so today, relations, domain, and range, and we'll probably get onto functions as well because it's very good for us. What is a relation? It is just a set of ordered pairs. What is an ordered pair? It's a pair of numbers written down in an order. You're used to seeing ordered pairs, you just didn't know they were called that. They're coordinates. Coordinates are ordered pairs because the x always comes before the y, so they're in order, and that means something. The order means something. A relation is any set of ordered pairs. Here you can see they've actually defined them as a set. So you've got set S equaling that first bit there. These earphones are not behaving. I'll try and put them there, that'll work. And set T, again, a set of ordered pairs. That's not the only way we can define relations. We can define them in other ways. You've seen y equals, 2x plus 4. That line is a set of ordered pairs. How many ordered pairs? Well, if I'm dealing with real numbers, there'd be an infinite number of them, wouldn't there, on that line? If I was dealing with just integers, there'd also be an infinite number, but it would only be at integer values. It's a good look, isn't it? Okay, so a set of ordered pairs. Within the ordered pairs, each set gets a different name. The first element in the pair is called the domain. You think of that as your input into the relation. The range, we think of that as the output. So we put numbers in, and then we follow whatever the rule is, and it puts out a number as the output. So, for instance, in set S that we have there, the domain of S is going to be 1. It's going to be 1 again, but I've already written it. I don't need to write it again. 3 or 5. That would be the domain of S. The range for set S are the second elements, the set of the second element. So it's going to be 1 or 2 or 4 or 6. 1, 2, 4, or 6. So domain, the values that you can put into your relation, your rule. Range, the possible values you can get out of your rule.
Make sure you know that one.
So that's going to become very important. So we can define them by writing out the set of ordered pairs. We've already seen that in those examples for S and T. How else could we do it? We could give a rule. So that rule is saying I have a set of ordered pairs, X and Y. How do we read the little colon? We read it as such that. So I want the set of ordered pairs such that the Y value is always equal to X plus 1. So it's just following that rule. Y is equal to X plus 1. So I want all the ordered pairs, X and Y, such that Y equals X plus 1, comma, and here they've given me an extra bit of information. What have they defined there? They've said my X, do we remember what that little curvy E stands for? Is an element of.
You have to be able to read this in an exam and interpret it.
So they want XY such that Y equals X plus 1, where X is an element of the set 1, 2, 3, or 4. From that, do you think we could write out the set of ordered pairs that would make up this relation? I think we could. We could say, well, X could equal 1. That's one of the elements in the domain that X is allowed to equal. If I put that into the rule, what's the corresponding Y value? 1 plus 1 is 2. If I put in 2 for X, 2 plus 1 is 3. You can see how that pattern's going to work, right? If I put in 3 for X, the Y value is 4. If I put in 4 for X, the Y value is 5. That is another way of defining that relation. It's the same thing, it's just a different way of writing it. obviously, if you had a really big set, writing out every ordered pair is going to get pretty annoying, especially if it's just y equals x plus 1 where there's no limit on the domain, because then there's an infinite number. I can't write them all out. A third way we can represent that set is to actually draw a picture of it. Do a sketch. Do those dots represent the same set of coordinates? 1 and 2, 2 and 3, 3 and 4, 4 and 5. They do. So that's another way of representing that relation. See the little note there? Why did they only graph the individual points? Why did they not just draw y equals x plus 1 is that line going through all the points? Why didn't they bother drawing the whole line? Go on here, tell me. You got an idea why. Why didn't they draw the whole line through all those points? Why did they only draw those 4 points? Yeah, because they restricted the domain to just 4 points. Exactly right. Perfect. I knew you knew. Just getting nervous. It's all right. It's not like cricket on the weekend. You can be nervous for that. Did we have a win? Like I said, be nervous for the cricket. All right.
So can we all appreciate then that because our domain is just integer values, there's nothing exists between 1 and 2 in terms of x. We are told it's not to be considered. Like 1.5 is not to be considered. So that is why we have to draw the dots, because there's no joining them up, because any values between them are not to be defined.
If it was defined differently, x, y, such that y equals x plus 1, where x is an element of the real number system. Real numbers, any value that exists on my number line. Well, in that case, I would have put arrows on the end of my little line there. It's going to be any point along that line. So my domain for that particular one, they've already told us, what would my range be? What possible y values can I get using that rule? Anything positive and anything negative and 0 and rational or irrational. Couldn't I get any number? If you look at your y-axis, if the y-axis represents every number, does this arrow imply that my line is going to keep going up forever? So eventually I could reach any y value, couldn't I? This arrow down the bottom, does that imply I could go as low as I want? Absolutely. So my range in this case would be y is a real number as well. In the first one, my range is restricted to just 4 values. What were the values? 2 or 3 or 4 or 5. All right. So we're going to have a look at some other ways of representing functions. They're always the same thing. It's just telling you, here are the numbers I put in, here are the numbers I get out. What other ways could I represent relations? These are called arrow diagrams. Let's see if we can make sense. We understand how a set of ordered pairs work. What possible values are in my domain? A 1, a 2, or a 3. So my domain on the left there consists of just the values 1, 2, and 3. If I start with a 1, what value does the relation go to? Well, there's only one ordered pair with a 1 at the start, and it goes only to the number 2. So you can see that section there, I should use my highlighter, that little part of my diagram, when it behaves, corresponds to exactly that ordered pair, doesn't it? Let's look at what about if 2 was the first element in my domain? 2 can map onto either the number 5 or the number 4. What does that look like in an arrow diagram? 2 going to 5 or 2 going to 4. Can you see the other two, 3, 6 and 3, 5, how they would follow the same thing? The arrow just tells you where to start and where to finish up. The one on the right, different set of things. Each number is only going to one possible answer this time. 5 goes to 4, 4 to 3, 3 to 2, 2 to 1. But it all works pretty effectively. That's all there is to really the starting definition of what a relation is. It's just a group of ordered pairs. There are other ways I could define them. They've shown you sets, graphs. I could just explain in words a relation. What about if I just said the set of ordered pairs in the second quadrant? What's that going to look like? Need to have dashed lines because it's not allowed to equal those values on the axes. Quadrant 2 is over here. It's going to be, I would just shade in that entire area, wouldn't I? And any point that is in that quadrant would satisfy that relation. It's still a relation. Nothing wrong with that. I could have said the set of ordered pairs exactly 2 units from the origin. What would that look like? I'm bringing this one up because I know we're interested in these things. If I've got my origin here, where are all the points that are exactly 2 units? Are you all happy that if I went to 2 on the y-axis, that would be 2 units away? 2 on the x-axis, -2, -2. Those points all match. If I wanted to do all of the points though, assuming I could draw beautifully, wouldn't I just end up getting a circle? That's a relation which I could define using my x squared plus y squared equals 4, x squared plus y squared equals r squared being the equation of a circle, or I could define it in words. Still relations, still a set of ordered pairs, lots of ways of defining them. As long as you follow the rules, you'll get the right bits. That's the first little section. They make a little note here about a maximal or implied domain. You notice in some of the questions, they are telling us what the domain is. X is an element of R. X is an element of the set 1, 2, 3, 4. If there is no indication in the question as to the domain, then you assume it's for every possible number that would give a value. That's all it's trying to say. So, when might that not be the case? If I have, we'll maybe do 2 examples here. If I've got y equals 1 over x, what is the implied domain? X could be greater than 0. Could I have even more? Yeah, which is what you were getting at, isn't it? Yeah. If I could have negative numbers, I can go 1 divided by a negative number. I can go 1 divided by a positive number. But what's undefined in maths? Division by 0. So in this case, my implied domain would be x does not equal 0. X can be any other real number. Can you see how that works? So with a domain, that's one of the things you look for. There's really only, well, there are probably 3 things that eventually we'll look for. There's really only 2 at the moment. We've got that one.
I'd write it like that though. Well, same thing.
Yeah, you want to write it with a slash? Yeah.
Yeah.
So the other way you can write it, x is an element of the real numbers, excluding
I think it's
0.
Yeah. And then you have to put that in curly brackets, don't you?
Yeah. So that's another way of writing exactly the same thing. So the little slash meaning excluding whatever comes after the slash. One more that we might be interested in finding an implied domain for. The sort of questions that would come up commonly.
Oh, and logs.
Yeah.
Make sure you got notes for these, you'll need them.
Y equals the square root of 3 minus x. What do we know about square rooting? What are we not allowed to do in the real number system? Can't square root negatives. So how would I write that? What would be the implied domain here? Yes, some of you will be able to see it, but here's how I would always do it, just to make my life easy. 3 minus x must always be greater than or equal to 0. Is that fair enough? Whatever's under the square root sign has to be greater than or equal to 0. And as Jay helped us out there, I think I heard a equal to as well, didn't I? I did now. Yep, that's good. X would be less than or equal to 3. X is a real number. The other one, which some of us will have done last year, but not everyone will have done. What about y equals the log of, let's make it 2x plus 3. If you haven't done logs last year, that's okay. For those of us who have done logarithms, when we find the log of a number, what do we know about the number? It has certain restriction on it. Yeah, well, I can have any base. I'll put it base 10. There you go. What do I know about the 2x plus 3? If this is going to be able to have a value, what do I know about 2x plus 3? Try it on your calculators if you've forgotten. Do the log of a few different numbers. When are you getting answers? When are you not getting answers? It can't be 0 or negative. Yeah, if we think back to our graph of these things, what does it look like? Y equals log of x looks like that. Yeah, so 2x plus 3 has to be greater than 0. Now, if you haven't done logs before, that's okay. You didn't need to know that. But I would expect you to be able to go from 2x plus 3 is greater than 0 to a simplified version of that. So what does it mean for x? Because I don't really care what it means for 2x plus 3. Let's rearrange it until we get x. 2x is greater than negative 3. Then I'm going to divide by 2. That is going to be my domain. X is greater than negative 3 on 2. X can be any real number, as long as the first condition is met. Those domain questions, you'll get heaps of practice at them over the next 2 years. It'll become second nature. You just have to really think about what are the things I'm not allowed to do in maths. I'm not allowed to divide by 0. I'm not allowed to square root negative numbers in the real number system. Can't find the log of a number if it's not positive. All of 7b is to do with that. You'll see here I put a very unobtrusive 7c here, where we talk about functions. Good news, functions are just special relations. Just like you have special rectangles, a square would be an example of a special rectangle. Yeah? Because all squares are rectangles, but they're special ones. They're the ones where the sides are of equal length. All functions are relations, but they're special ones. And they're special because every element in the domain maps onto at most one element in the range. Functions are special because they're consistent. If I put a number in, I always get the same the same result out of the function. That's what's special about them. Sometimes rules will do that. We saw up here, this first rule on the left, that would not be a function because when x equals 2, there are two possible outcomes. Or outputs. That is not a function. When I consider the one on the right, each element in the domain maps onto at most one element in the range. Therefore, that diagram represents a function. So functions, special relations. If I have an x value, an element in my domain, it only goes to one possible answer in the range. That's it. That's the only special rule. Some of you who are quick at reading would have seen, what's that vertical line test it's talking about? We don't always have our functions defined by sets. Sometimes we have pictures. The vertical line test is a quick visual way of looking at a graph and determining, is it a function or is it not a function? Because what does a vertical line represent on a graph? Doesn't it represent one x value? The equation of a vertical line is x equals a number. So if we consider a few different graphs here, let's have a look and see which would be functions and which would not.
All right, I'd like you to start now. Question 1, is it a relation or a function?
I'll give you one more minute. Go. All right, so we've had a look, and all you do is you picture a vertical line traveling from the left to the right across the function. So long as it never touches the graph more than once, it's going to be a function. So it doesn't matter where I draw my vertical line in this first one. Wherever the vertical line is, does it ever cross the graph more than once? No, so it is a function. What about the next one, x equals y squared? It's okay over here. There's no value, that's okay. It's not going to more than one. There is at least one case where a vertical line is touching the function at two different spots, touching the graph at two different spots. So it's not a function. It is still a relation. It's still a set of ordered pairs, but it's not a special one. It's not a function. What about our circle? Not a function. You can see the y-axis is already a great example. We could put another vertical line, and there are an infinite number of times where it will touch 2 points. So not a function. Here I have, do you remember what this sort of function is called?
It's a very wise type of function. Piecewise.
Piecewise defined function. Piecewise defined functions turn up in things like car parks. Wherever you stay for 0 to 2 hours, it might be free, so the cost is 0. Then between 2 and 3 hours, it might be $8, and then 3 to 4 hours, it might be $12. So they have different rates depending on how long you stay there. Usually they are functions, but you can see in this particular case, when x equals b, there are two possible outputs. Therefore, that is not a function. So, summary. What have we done today? Relations, sets of ordered pairs. That's all they are. All of the first elements, the set of all the first elements is called the domain. Set of the second elements in each ordered pair is called the range. We can define relations in lots of different ways. We've got graphs, we've got drawing the sets, we've just got naming the ordered pairs, we've got mathematical rules and equations. All of those are okay ways of doing it. We've got arrow diagrams as well. We've got words. All of those things can define relations and functions for that matter as well. But the functions have something else special going for them. Functions, whenever you put in a value, you get at most one value out of the function. Relations may map onto more than one value. Finally, the implied domain, what are the three things we're looking for? Can't divide by 0, can't square root negative numbers, and we cannot find the log of a number unless that number is positive. That's all there is to it. We are going to do a little quiz now to make sure you understood what we were talking about.
Okay, before the quiz, everyone have a thumb war with the person sat next to you. You've got 2 minutes.
Oh.
Quickly.